psi is total, represents our entire system, the entire system. There's just one psi. But because of approximations, we can reduce this to the psi of the nucleus and the psi of the electrons. This is based on the Born-Oppenheimer approximation because the nucleus is uncoupled from the electrons. Back to that picture of the two rhinos. One rhino moves, all the mosquitoes move with it. They don't even notice. They just keep on moving. And I should say they're uncoupled mostly. They're mostly. You'll see that they're not really uncoupled when you do the HCl problem. But we can, but in the same regard, or in the same way that we do the orbital approximation where we have one wave function for multiple electrons, now we have one wave function for multiple types of motion. Okay, so what we can do is we are going to then take, and actually I'm not even going to take H psi is equal to E psi, I'm going to take the expectation value of it because I want to know what my total energy is, not what it could be, which would be all of the different options. But I want to know what it specifically is, because if I know what this wave function is, or this Hamiltonian is, and I know what this Hamiltonian is, expectation value, then I can find delta E. I'm looking for the difference between the two. Okay. So let's take the whatever this is called, expectation value of the total energy of this bad boy, psi total. But first, before I do that, actually no. So this would be integral psi total star H psi total d tau over all space. But my Hamiltonian, think about what the Hamiltonian is. Your thought is probably, well, what system, Allison, are you talking about? Well, go team, think about it. For vibrational, what would be your system that you would use? Harmonic oscillator. What about for rotational? Particle on a ring is really the only one that you can probably think of at the moment. But there's another one. It's called the rigid rotor, where this is just rotating like a dumbbell. Quantized. Anyway, so go team. So rigid rotor. Well, electronic. Think about hydrogen, just a hydrogenic atom. Nucleus. We haven't talked about nuclear spins yet, but it has its own wave function. And Hamiltonian. Okay, so what we're going to do is we're going to say that this is and all of those energies are added together. Potential plus kinetic, plus potential, plus potential, plus potential. So we're going to have vibrational plus the Hamiltonian of rotational, plus the Hamiltonian of electronic, plus the Hamiltonian of the nuclear. Go team. So when I put this into here, I get psi total H vibrational psi total d tau plus psi total H rotational psi total d tau plus da 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 da. Go team, that should be a d tau. And I have one of these for every Hamiltonian because they're all added together. Okay? But, and you could do this looking deeper on every part of this. But when I look close here, I get, so this whole thing equals integral psi vibrational H vibrational psi vibrational d tau. And this one equals psi rotational H rotational psi rotational d tau plus. And you might be like, well, Allison, why is that? Well, let me show you. So what you would end up doing is the most ridiculous, like, expansion of this. But it turns out that because all of the other wave functions are orthogonal to one another, the rotational and vibrational wave functions are orthogonal to one another, they are going to be zero when you have something that looks like this. So if you had psi rotational, H vibrational, psi rotational, that's going to equal H integral. So this Hamiltonian does not operate on that wave function. It doesn't, it can't, because it doesn't satisfy the Schrodinger equation. This Hamiltonian is not associated with that rotational because it's vibrational Hamiltonian. Does that kind of make sense? So what happens then is you get psi rotational, psi vibrational, d tau. And this part right. And so, oh, sorry, those should both be rotational. Go team. Vibrational. Awesome. So this part equals 1 because it's normalized, and you're left with just the vibrational Hamiltonian. That made, sorry, I got my rotational and vibrationals mixed up. And so for when you're operating on the rotational part of the wave function, you don't get, you only get the Hamiltonian back out again. And even more, when you're integrating V vibration or psi vibrational, psi rotational d tau, you're going to get 0 because these are orthogonal to one another. Go team. Okay, I'm going to pause for a second. There you go. You can pause and look at that closer. Okay, so when I take, so from what I just did, now I'm going to look big picture back again. So with H total, psi total, when I get this, it reduces down to just 4 possible equations. I'm going to get H vibrational, psi vibrational equals E vibrational, psi vibrational, H rotational, psi rotational equals E rotational, psi rotational, H electronic, psi electronic equals E electronic, psi electronic, and any guesses, nuclear, psi nuclear equals E nuclear, psi nuclear. Go team. Okay, this is the Born-Oppenheimer approximation. Rhinos and mosquitoes yields this, okay? So what we end up then getting, which is unbelievably fantastic, the expectation value is going to then be E total, which equals E vibrational plus E rotational plus E electronic plus E nuclear. Go team. All right, for those, actually I think most of you took thermo with me. Go team. That's you. There's your internal energy. And these are, assuming equal partition, 1/2 kT for each one of these. Statistical mechanics tells us that 1/2 kT does not work because not all of these energy states are created equal. But this is what the total energy is. It is the internal energy of your system. Ta-da. Okay. This is why I like quantum first, because I can be like, this is you. Go team. Okay. So the nice thing about this is that you get different energies from each of these different H psi's equal to E psi. Sorry, the handwriting's crappy, but deal with it. Okay. This comes, so from these systems, we are going to get energies of vibrational, okay? Those energies are going to be associated with a transition dipole moment of the dipole moment derivative. And it gives us IR. The energies associated with this transition, such that the wave functions that represent molecular vibration, gives us energy differences in the IR range. Rotational gives us microwave. Electronic gives us UV vis. The nuclear, we actually have to be in the radio, but we will be in, that's how we get nuclear spin states. Right. The kicker, though, is that these can couple together. Their energies are actually not that different, but the energy associated with the electronic is far enough away from the IR that you can essentially uncouple them, but there's going to be some subtle nuances, and this is what being a spectroscopist is all about. It's understanding how do these electronic states or vibrational states or rotational states, how do these wave function states change upon superposition and an angular momentum transfer from a photon? You've got a boson interacting with a fermion. That's weird. And when you do that, you have a change of state. And that change of state can be represented by these independent Schrodinger equations, but sometimes they can't. And that's what you'll see. You'll have a coupling between these two for your HCl-DCl problem. It's really fun stuff. Okay, that's all I got for now. Go team. Born-Oppenheimer gives us this. Oh, what are we going to do? Okay, so this is spectroscopy. Each one of these, this is the last, well, this is almost the last of the quantum mechanics that we'll get into, but each one of these is going to have a different, so harmonic oscillator, rigid rotor. All of these are going to have selection rules. Delta V is equal to plus or minus 1. Delta J is equal to plus or minus 1, or delta J is equal to 0. All of these are going to have selection rules that come from the transition dipole moment operating on the wave function. They're all going to have energies that are going to give us delta E's. We're not doing the quantum to get these. Atkins does that for us. We're going to use these delta E's and the equations associated with the quantum numbers of all of these different quantum states to understand the spectra. Cool? Listen to that a couple times and it'll make more sense. That's all I got. Bye.